Join us on a voyage through the wormhole, your gateway to groundbreaking thinking on AI, space exploration, a healthy planet, and a more intelligent future. I'm your host, Jonathan Knowles.
The Wormhole is produced by Trillium Technologies, leading the application of artificial intelligence for planetary stewardship, space exploration, and human health. Help us explore what's over the event horizon by following us on LinkedIn and Twitter at trillium.tech. Together, let's build an intelligent future.
This one is particularly exciting and fun for several of us who are on this today. You're going to hear from some wonderful experts with regards to Apollo's legacy, and specifically Apollo's legacy for AI. Today, we will hear from our experts as they all delve into how the stringent safety standards and trust protocols of the Apollo space program can really inform us on the development of secure and trusted AI systems. Today, we'll highlight vital lessons from space exploration to ensure reliability and safety of artificial intelligence. We're going to go through very quickly a few things to set things up. As a reminder, Trillium Technologies, the Frontier Development Lab, is a NASA partner. We have for 10 years now been at the intersection of space technology and advanced AI research with a variety of partners who have made this possible, including Google Cloud and NVIDIA. This all got started by honestly, I came across a report called What Made Apollo a Success. It was produced in 1971. It was I think, 87-page report, and it went through answering that question step by step in the way only NASA can do something like that. And it was just interesting. So I shared that, and the person I'm about to introduce here, as a matter of fact, I'll go ahead and bring him up while we do this. This is James Parr. He's the CEO of Trillium. He's the founder of FDL that we got going 10 years ago. My goodness, James, 10 years. So James read this report, and he had the insight that, wow, we really could take these principles and apply them to what we're doing with regards to AI systems. So this whole concept of comparing and learning from came from James. And I encourage everyone to read this report. We'll see if we can find an easy way to share it here, or you can find me on LinkedIn at Jonathan Knowles, and it's in one of my posts. I'll try to highlight it there afterwards so that you can download the report and read it yourself. If you're interested in space, I think you will want to do that. What I'd like to do, actually, before we get started with the principles, James, that have been extracted from this report that we're going to talk about today, I'd like to bring up someone who was with us at the beginning when we founded FDL. Let's bring John Karse up. John is a former NASA scientist. He has been engaged over the years in many aspects of this, but even more importantly, I think he falls into the category very squarely that I know James and I, and actually all of our speakers here today, do. Space nerd. Wouldn't you say that's true, John? Yeah,
very
welcome.
Yeah.
Thanks for joining.
With pride. Yeah.
With pride. You know, I think I'm probably the eldest of us here on the Zoom today. And I'm going to try to share this. Those of you who can't see the Zoom, I'm holding up the Apollo 11 t-shirt that I wore as a child watching the Apollo 11 moon landing. My mother had managed to save that shirt, and I still have it today. So I think we're all a bit nostalgic whenever we're talking about the space program in the 60s and 70s, especially the Apollo missions. It was such a big deal. It was actually quite audacious when you think about it. And so we tend to save little bits and pieces of things. And of course, James is in London right now at the Trillium offices in London. And You're in a space library, aren't you, James?
Well, I was going to say, I'm going to raise you with your Apollo T-shirt. I'm actually in the space library in our offices, and it is the world's oldest space library. And actually, I thought I'd bring a prop here for everybody who's watching. I don't know if you can guess what this is. John, can you figure this out? Probably. This is really, really heavy.
Is it some sort of turbo pump or something?
Wow.
Yeah, okay, all right. Yeah. That's no fun playing with you, but it's a rocket turbo pump. But it's incredible how heavy it is. Like, this thing is, you realize how much pressure it has to withstand. It's phenomenal.
Yeah, it really is.
What's it from? Do you know?
It's from the DH Spectre. It's a hydrogen peroxide turbo pump. Yeah.
Sweet. All right.
Yeah.
Well, I can't say I'm in a space library, James, but can you guess whose office I am in?
Gene Kranz?
That's exactly right. Although not really. This is an AI version of what I thought Gene Kranz's office might look like, and that's why we have those words "tough" and "competent" up there behind me on the blackboard. And John, you're joining us from the East Coast. I'm here in Silicon Valley, in California. As I said, we're all space nerds. John, just for a couple minutes, and all of us actually, but I'll start with John. Let's talk a little bit about what's the big deal about the moon. Why does it matter? I mean, I have my ideas about why it's still exciting and that whole nostalgia thing. But there's, I think, a little something more to that. Wouldn't you agree?
Yeah, totally. And I should say, just before we get into anything, that like you mentioned in the intro, that I just recently worked with NASA, and I've moved on to working someplace else now. And just want to be clear that the stuff I say today, I'm representing myself, not NASA anymore or the federal government at all. But with that said, from my perspective, the moon itself is interesting for a lot of reasons. As our neighbor, as Earth's partner for the last 4.5 billion years, whatever it's been, and as a way, as a piece that can help us understand, Earth, our solar system, our place in it, and returning to the moon is important, both because it'll provide us new opportunities to study it and to help us expand our understanding of Earth's history, our history, and how they might be developing with time. But also because it, returning humans to the moon will be a next step in helping us move farther outward as well. That it will both give us an opportunity to learn how to operate in a new environment, humans have been operating in free space for a long time now, but it's only been for short periods that we've operated on the surface of the moon, and that's the only other planetary body we've been on. So from my perspective, it's really important that we learn how to operate in a new environment like that, and learn how to beyond the specific environment there, know how to organize the way we do things in order to live in new environments like that. That may be one of the most important things we learn. And then beyond what we learn, it could provide new opportunities for moving farther outward too, like the potential for resources to let us extend our reach farther out in the solar system. So I think it's really the moon and our return there are really important for a lot of reasons, both scientific reasons, but then ones pertaining to developing ourselves as a species, and then our ability to move farther outward.
Two very good points. And there are pieces of the Earth on the moon, just like there are pieces of the moon on the Earth. So we will literally be able to, for the first time as we spend time there, look at what the Earth really looked like 4 billion years ago.
I would love to find some old rocks, Earth rocks hidden away there.
Wouldn't that be something? And resources, as you mentioned, we know there's water on the moon. We can make fuel. And because of the gravity well of the moon, potentially launching is easier from there as we decide to go and explore other places. So for many reasons, James, what are your thoughts on why going back to the moon? And perhaps you can even just wrap in a little bit about some of the things we've done over the last 10 years at FDL that might be helping with that.
Well, I think I get excited by doing hard things. Like this is really, one of the things about extending your reach, which is the famous quote by Danny Hillis, who's one of my heroes, sort of AI hero. If you know about the gestation of AI, you'll know Danny Hillis was a big player, and but he said that it's always useful to extend your reach because by extending your reach, you create new things, and it's a sort of exhaust, if you like, and even the technologies we're using right now, whether it was the PC or the CMOS sensor, which is in our webcams, or even Unix, this is all outcomes of the space program. And so in a way, we're standing on the space program just by having this discussion. And so I get excited by that exhaust, the innovation exhaust that comes out the back of doing difficult things.
Nice. Love it. And I think that's why so many of us are interested in space and humans going out, is certainly all the things we've talked about, and the human desire to continue to explore and reach out, and the desire to make things better here on planet Earth. And I think we all have a vision for how space can do that. And I believe AI provides yet another one of the technology building blocks to help us do just that. And so today we're going to bring that focus down into AI. And as we mentioned, we're going to compare the learnings from the Apollo mission to development of AI technologies for space, but other things as well. James, I'm going to ask you to run us through just the framework very quickly, just so everyone has here's what we're going to talk about points. Mm-hmm. Then we're going to go through each of them one by one with our speakers today. So if you'll do that, that would be great.
Yeah, so it's perhaps useful to, to sort of frame what state of the art looks like in AI. And I can't wait to have Scott and Freddie join us on this, but we use the language TRL, which is from NASA and normally stands for Technology Readiness Levels. But with AI, in the end, it's about trust. It's about systems we can trust and systems which are safe. And so, perhaps we should start calling it trust readiness levels, because that's essentially what we're trying to do. So when we are trying to advance trust for our systems, we have to start applying really advanced engineering methods. And this is why the Apollo analysis was so interesting. So if we go to the next slide, we can go through these quickly. So the first one was attention to detail. Being really meticulous. Don't cut corners, make sure your code is beautifully annotated. These are just the real basics. Start with precision development, and that's really the first lesson. The second lesson is simple is sometimes best. Now, there's a lot of models out there now. In fact, there are hundreds created every week. But in the end, you want to have a system that can be used by other people, that can be easily debugged. You want to minimize complexity, especially if you have systems which are dependent on other systems. So the next lesson is just simple is sometimes best. The third one, and again, I love this about Apollo: test again, rigorous integrated testing, not just the single components, but the integration of the systems. And so end-to-end tests of all those integrated components is crucial. And certainly that's something that we're doing a lot more of now, is getting AIs that are working in concert. And so again, this absolutely plays to that. Point 4 is strict configuration control. So making sure it's beautifully documented, robust version control, change management. Again, every modification should be documented and reviewed, and we don't want any inconsistencies. And then lastly, the fifth lesson, extensive training and simulation. And if you're if you're listening to this podcast, there's a picture of the two simulators, the command module simulator and the lunar module simulator, and they were again very detailed simulators for the astronauts. So every scenario they thought through prior to the moon landings. And in AI, we call these edge cases. And so you want to think through every single edge case, understand the failure modes. And of course, if your model and your system doesn't adhere or doesn't work in a certain failure mode, then you go back to the drawing board. And again, this is stuff that Freddie and Scott will be able to talk to. So that's our playing field. And yeah, looking forward to jumping in.
Excellent. Let's get started. Let's bring up our other speakers today. First of all, I will introduce you to our colleague and good friend, Scott Penberthy. Scott, welcome. Thank you for joining us. Scott is the Managing Director of Applied AI in the Office of the CTO at Google. And we have been working together for many years now. And Scott has been providing advice and insight and been just a real big part of all of the accomplishments that we've had. And then we'd like to bring up Freddie Kalitsis. Freddie, welcome. There you are, Freddie. Freddie is a senior research fellow at the University of Oxford Applied and Theoretical Machine Learning Group in the UK. So Freddie, always good to see you. You've been with us for a long time as well. And I think you'll both agree we have a lot to talk about when we think about these tenets. Let's get started by doing lesson number 1, precision in development and paying meticulous attention to detail, every aspect of every algorithm, scrutinizing everything, regular code reviews through documentation and maintaining high standards. Scott, why don't we start with you? What are your thoughts on lesson number 1, precision in development?
I think this is a challenge for a lot of us, I think, Jonathan, as you get into it, because, for years, a lot of the software development, I was looking just back at the language that was developed for the Apollo onboard computer, and actually has commands like please perform, which I love. Right? And what's interesting is, if you advance to today, we're talking about large language models and transformers and some of the latest advances. What they're doing is taking complex systems and turning it into nouns and verbs and basically a dictionary of actions that a model can take. Right. And what's interesting is we were all fascinated with the large language models of transformer. We were too, but it reasons in a probabilistic space. It always hallucinates. It's just that sometimes it hallucinates and aligns with what we believe. Right. We call that truth. Right. And so what we're seeing now is that when you start to think about things like space missions and business and money and health, we're seeing the rise of this notion of a workflow, Jonathan, which is where you take a deterministic thing, like please do this action, like on the Apollo computer. But that deterministic workflow has steps in them that are basically can now be taken over by these AI techniques. And so that sort of gives you a deterministic outcome, even though a step itself may be probabilistic, right? And we're starting to see that's the idea where you now have AI as part of a system. We were all sort of enamored with AI and the advances. It's still extraordinary. I was just seeing this morning, some image models that came out. But what we're finding is that when you implement these, it's really part of a larger system. And that larger system, the AI is not acting more human-like than system-like, or systems that have bugs. So then we can apply all that we've done for the last 70 years, 50 years in space to now figure out AI is just another component of the system. And I think that has tremendous opportunity. And I think the things that you've done, James and Freddie and folks, you're looking at super resolution, finding iron ore on the moon and everything else. That's now a step in a workflow. And workflow is like a NASA protocol. And we have, decades of experience, Jonathan, in how we can actually manage protocols with humans that are pretty much unreliable, right?
Yeah.
AI is now just a part of that workflow.
Yeah. And so precision absolutely matters. And by the way, I hadn't until now when you said please as a command, this was actually noun verb was the interface for those who don't know about the Apollo systems on board. That was their little booklets of how to use the system would give them the list of nouns and the list of verbs. And that's how they were labeled. And it was exactly how they decided to work with them. And so precision absolutely matters when you think about things the way you just said. So, Freddie, what are your thoughts on the importance of precision in development and how we can apply that learning from Apollo to what we're doing these days with AI?
So my mind goes to the culture differences that exist in the field of the engineering of machine learning and in space engineering. I think there's just, from the moment that an engineer is trained in undergrad, in computer science, let's take computer science for instance, they don't really have a good notion of what is mission critical until eventually they do apply it in a mission critical, safety critical setting. In machine learning in particular, if you look at all the research that is being done, everything is benchmarked on imprecise goals. I mean, there's a goal of try to annotate this correctly. Let's try to increase the precision, the accuracy. Imperfection is okay. So it's literally like a one-upmanship culture where we're just trying to prove that I'm less imperfect than you are, and this is how development in AI is driven. But it's never about we must not fail at this, right? This is the way in space. But suddenly, when you're trying to make AI relevant for space engineering, there's this massive culture gap that needs to be bridged. And it's not that we don't wanna, or it's more like we don't know how to, because at the end of the day, the amount of data that we have and the parameters that we're dealing with in this unstructured data, because we're talking about images, we're talking about video, we're talking about text, all this unstructured data have so many parameters. It's a very ill-defined problem. How do you turn that unstructured data into something that is a useful cognitive result for a human being? There's so many undefined parameters. This is totally different from space, where you have a very well-defined goal. You know what success means, because otherwise you're dead. And you just strive to get there. In machine learning, it's very different. Also because there's the kind of products that we develop in machine learning. If it's for consumers, it's okay to be imprecise there. We can always iterate on the problem. We can get customer support. In space, you cannot get customer support. So I think what we get, there are lessons we can learn from how meticulous and rigorous space agencies have been when it comes to human safety. However, when you apply them in machine learning, it's just the cost-benefit analysis is completely different.
Yeah, James, I see you nodding quite a bit. Do you have any thoughts on this with regards to precision specifically?
Well, I was sort of just going to say that's the, and people may disagree with me on this, but that was sort of perhaps the problem with the assumption about self-driving cars when we jumped in that adventure 10 years ago. Whenever there was assumption that perhaps deep learning would be good enough, but getting to that last little bit has been so difficult. But yeah, John, I'd love to hear your point on this as well.
Hope you're muted, John.
Of course I am. So, Freddie just in the last moment said a word that was really on my mind. That even more than precision, I think the word that I would go with is probably, in terms of what's really critical, is rigor. And as everybody's been saying so far, what we're talking, to achieve trust in the system, in an AI system or any other system that we build, really requires actual engineering. We need to design the system to reliably provide an outcome that we intend without extra surprises. And that's different from the way a lot of software development, as Freddie was saying, that's different from the way a lot of software development has traditionally been done. It's gone through phases. And if you look through, the history of it back to the Apollo era into the 70s, there was a lot of, the spacecraft engineers would use the term systems engineering. There was a lot of systems engineering in software back then, and for a lot of purposes, that's overkill. And there are more cost-effective ways to achieve the ends you want to achieve with software. That you can develop systems that are appropriately trustworthy without going into the really intense level of rigor that's gone into with spacecraft. And that rigor goes kind of at all levels through the development process. It's again, to what Fred was saying, part of it is, it's determining the goals. That at the very beginning, the first things you do are kind of understand what goals are within reach, technologically, physically, resource-wise. What goals are within reach? Which ones do you actually want to bite off with this mission? And then once you have the goals, that helps you then start to understand things like, okay, that's what we want to achieve. How do we come up with a way to test, as you were saying earlier, that we have a system that, what capabilities does the system need to have? What traits does it need to have in order to achieve those goals? And then how do we develop ways to test it in order to achieve that? And, this entire process is, whenever somebody's conducting a space mission, they go through that in a very stepwise fashion to build up from the earliest understanding of what it is that you're trying to achieve, all the way through, okay, what does that mean in terms of the capabilities we need to get to and how do we test them? And then you really get into, okay, the development of the actual system that's going to carry out. That's an intense amount of effort. And valuable when you're building really complex systems. And so, part of the art here, I think, is going to be understanding what level of rigor, what level of precision is valuable to achieve certain is important for achieving the objectives that you want. And so it gets back to really understanding what those objectives are. So, I would say precision, rigor, those are actually part of your objectives that you need to choose also. And so, and when you're working on a self-driving car or, an AI to run a flight system or something like that, you might have a very different bar from, if you're, making a recommendation system for what flavor of ice cream you want next. It's, you have to choose the level of rigor for the problem you're trying to address.
Nice.
Well,
James, you're ready.
Hull was all about objectives, wasn't he? That was the problem.
So perhaps insufficient analysis of how trustworthy that system was applied there.
Yeah, we'll do another wormhole on AI from sci-fi movies, by the way. So, by the way, okay, so you talk about complex systems. My goodness, when you think about the components, you think about the rocket, the Saturn V rocket, and you think about the command module, the lunar module, and all of that unbelievably complex. How do you do simplified architectures in systems like that? And more importantly, AI systems, they really, I mean, the way we do AI really is complex, but the way we're trying to develop these things, we do try to approach with simplified architectures and simplicity. And I'd love to hear from Scott, then Freddie, on that particular topic from lesson number 2, simplicity in design. How do we do that?
How do you do simplicity design? I think rapid iteration and I think if you look, there's a very famous photo of SpaceX. Here's the first version of the rocket engine and the latest version. It's a beautiful piece of engineering. We're seeing the same things now in a lot of things in AI systems, right? We're starting to see them deploying, saying, well, you basically have an inference network. You've got some sort of memory, some sort of storage. I'm like, yeah, that's kind of right. And is it RAG? Is it context? Is it local? Is it storage? Is it tensor? Well, no, it's kind of like your AI network that you're inferring from, some notion of memory and storage. Sounds like computers from 1960s, right? And yeah. I think as we iterate, Jonathan, as a community, we're starting to see these patterns. and the patterns are starting to hold true. And now we're starting to have a more fundamental understanding of how to use these tools. And I think, back to the comment about John and precision, it's almost about accuracy versus precision. There's this big obsession today of, well, how are the neurons firing? What neurons fire to give me this result? How do I get accuracy? I think it's misguided, right? AI is not a tool. It's not an API. It's a collaborator. So if your AI is collaborating for your engineering, that's how you use it. So the human still makes the decision. AI helps you. Likewise, if you put AI into a system, we treat it much more like what Freddie said, is that it will make mistakes. It's probabilistic. It's not deterministic. So now you're creating the systems where now you can deploy a new type of intelligence, almost like an alien intelligence, in that system. And back to John, how do you create a system that now it's not just humans, it's humans and AIs working together to solve it, but they're probabilistic. We could chase our tail trying to figure out how the neurons fire and what's going on, but instead shift to thinking about, no, it's a collaborator. Let's bring it in. How do you now deal with humans? Now AI is another thing to deal with.
And we've had conversations, Scott, about that super important point you just made, especially with regards to trust, as James brought up at the beginning here. And in the same way, your human collaborator might walk in and it's somebody you don't know, but has some background and some experience, and you may not have some level of trust with that human. In the same way, we're starting to experience a bit of that with the AIs. Why should I trust this thing? Very similar to why should I trust that person who is going to collaborate with me? But once we wrap our heads around this, I think that's a real important way to think about our relationship with AI going forward.
Right. And who do you want advising the astronaut on the moon? Someone who's seen 1 million cases and every genome on the planet and all possible cases that have been released by all governments, or your local doctor who's seen 16?
Yeah.
And it's sort of that's kind of where we're headed, Jonathan. And I think we get into discussions more about trust, but I think that's sort of a mental shift that James has been also leading, is how do you bring these probabilistic systems and reasoners into space systems? Because they're fantastic, but they're fallible.
Yeah. Freddie, I'm curious as to your thoughts on simplicity in design as a learning tenet from the Apollo mission.
I don't know a single thing about rocket science, but one thing I know is that the AI is really simple, actually. Like, I think it's a testament, the fact that so many people can get into machine learning by at least the basic principles and start, learn to do the first Python program in PyTorch in a matter of days, if not weeks, if they're a beginner program, that is. Then it's a testament to the fact that machine learning, or AI, as we use it now interchangeably, it's governed by very few principles. The working underlying principles, like the workhorse of modern machine learning, comes down to like 2-3 things. Backpropagation, and neural networks, and I don't know, I'm missing the third one, but I think, and then everything from there is just like recombinations of the same concepts. I mean, even transformers are made out of attention blocks, and attention blocks are made out of neural networks and basic matrix multiplications. All of these are components that we've known about for decades, but we just realized that the particular recombination makes sense for the kind of data that we have in large amounts of text and whatever, and vision. But the principles will remain the same. So in that sense, I argue that AI and machine learning in itself, the governing rules, if you look at it like, the laws of physics, not the laws of physics, but the laws of machine learning, are pretty simple. Just like the laws of nature are pretty simple, Newtonian physics, underlying rocket science. But then complexity comes in not through the AI itself, but when it taps on the data. The real complexity lies in the real data that it's trying to learn from, because there's just such a richness in the patterns of our complex and structured data that we have on the internet, videos, text, and sounds. Yet the simple governing patterns of machine learning can tap into that and tease out those patterns. But the patterns themselves are very complex, and there's just so many of them. So it's not really that we don't understand AI, is we don't understand what the AI is trying to tell us in the end of the day. That's what we have a hard time understanding. On the other hand, we can tell very well what a rocket is trying to tell us, because we can read out the sensors and how well it's performing and all that stuff. So I think there is a very, very different paradigm here of a scientific understanding of these different disciplines.
You know, that feeds very nicely into the next tenet, which is rigorous and integrated testing. As a matter of fact, when you read the report, the author of the report calls out that this is the most important tenet of all of the things in this report is test and test and test again. How does that fit into what we're trying to do with AI, considering we have so many of these unknowns? And considering the leaps and bounds that we are seeing with regards to our advances, I'll just open that up and say, who has some thoughts on test, test, and test again, and how important that is for AI development? Scott?
Test, test, and again. I think it's each epoch in machine learning training essentially is a test. Think of it that way, right? So think of, the trillions of tokens you're pushing through a transformer, right? Here's the input. We expect to see the output. How you doing? And if you make a mistake, it's called loss. We track the error loss, and now you get down. And what my point earlier was, loss will keep going down and down, which is like trillions of tests of the network. But the final ones, it's never perfect, right? And so we'll strive to get that really close to the asymptote. You're seeing the things now with diffusion models. I think maybe Freddie were talking about what's in addition to machine learning. The physicists came in and now said, "Oh, diffusion's pretty cool. You can add that now, right?" But as you get really close to the asymptote, those tests run, but you're always going to have this gap, right? So if you test and then they have the more standard, unit code tests and other things for the testing for the software. But that's kind of new, because essentially training is a massive test of your network, right? And then you test it against the golden standard, right, which you don't touch, and that gives you evaluation of benchmarks, that Freddie said, right? But I think the tough thing for us is a culture divide, which both John and Freddie talked about, is how do we now accept that we have a probabilistic result, right? We somehow seek comfort saying a given module passes all unit tests, but it's fallible, like the O-ring. Things happen. Right. So how do we then deal with these probabilistic systems in our classic way of training these? And how do we accept that? Because we accept humans, and we have this comfort of, well, pass all tests, it's going to work. Well, metals fatigue, there's space debris, stuff happens. Right.
Yeah. Very good point. Freddie, do you have any thoughts on that, following up what Scott just said?
Yeah, we're very good computer scientists. We love our metrics, and we love to compare in a community. It's like, as I said earlier, there's this one-upmanship culture. If there's something that we can measure, then this is how we iterate through the game. But I think at a meta level, I think the ultimate success of any system is based on a goal that we do not have. We cannot attain it. We do not have the goal, for instance, of the success of a rocket in space until you actually get to do it. There's a similar notion in machine learning, but I think there is not just the fact that we haven't done it yet, because at least in space engineering, we can create a simulator. We can simulate a lot of things, even the hardware systems. But in machine learning, you cannot simulate a model going into the wild and its impact in society. You don't have that. And also, you have to be a little bit more precise. We know how to train models because we can define mathematically so-called objective functions. So, for instance, when we're talking about image detection, object detection, a good model is one that detects an object. So, therefore, we know the ground truth. We can see what the model predicts. If there's a match, we have a particular metric to measure these matches. It's a good model. So we iterate based on that objective function, and we compare with everyone in the community. So, but ultimately, the meta goal, what is the meta goal of such a model? how is this being consumed by the public? That you cannot codify with a mathematical function. So I think there is this concept of the attainable goal, the unattainable goal in machine learning, where we always have a proxy that approximates the real goal. But it's always within this, like, if you look at the set of all goals, then the only goals that we can use as proxies is the ones that are mathematically definable. Outside of that set, the rest of the subset is like, the things that you cannot codify. And then, probably we can touch on things like ethics and fairness and bias and all these other things that our community is trying to codify. It's trying to look for these other goals in the rest of the set and trying to find mathematical descriptions, ways to optimize with respect to those fairness goals and bias goals.
Thanks, Freddie. James, I saw you nodding quite a bit. Or John, it sounds like it seems like you might have something to say on that as well.
Just a couple quick thoughts that are close to what Freddie was just talking about. That when you think about tests in space systems, that they have to follow from a particular objective. You choose your tests to make sure that the system is going to be capable of achieving what you want it to do. And so the discussions of what are your goals and what are your tests are tightly intertwined things. And they also evolve at some level as you understand the system. And in order to comprehensively test something, getting back to the previous discussion, you only really have a shot if you're working with a relatively simple system. If you've broken it, if you've decomposed it into smaller pieces, and you can develop tests at the smallest scales and then build your way up. Whether we're talking about the internal workings of a transformer or of an AI, system that's being applied as a component of some other engineered system, we need to understand what are the goals of the pieces that we're talking about. What are the tests that ensure that we meet them, and whether that's in a very yes, no sort of sense, or in terms of a probabilistic distribution, say, they have to follow from each other. Another thought along these lines that comes from the space community, a mantra that's employed all the time in the space community, is test as you fly and fly as you test. And that means, as you're planning, as you're developing a thing, understand how you're going to use it. To what Freddie's saying, do your best to understand how the public's going to use it, and just design your tests with that in mind. And then when you're actually using it, try to stick to only within flying within what you've tested. Otherwise, when you deviate from that, you're courting trouble. That's when you're likely to have issues. And so I would say, if there's a mantra to steal from the space world regarding testing, beyond test, it's test as you fly and fly as you test.
Great. Thank you for sharing that mantra. James, did you want to jump in?
Yeah, I was just sort of imagining, I'm wondering if we could somehow put the test dynamics into the meta tags of an API or something. And the reason why and perhaps this is possible, and Scott and Freddie would be like, yeah, we do that all the time. But what I was imagining is, the problem that modern doctors have, where imagine a Punnett square, which is 1,000, x-axis is 1,000 and the y-axis is 1,000, and each one of those squares is like a treatment and a genome, and there's a efficacy and there's a cost. And this is why modern medicine is so difficult for human beings. We just don't have the cognitive capacity to understand the solution set. But Scott, when you were talking, I was imagining an LLM could do this. An LLM could start deciding, well, this is the right sort of component, deterministic component, but it needs to know the trust aspect. So if we sort of started building sort of trust into the API, somehow built that into the AIs, we could start using this sort of community of AIs to sort of start sort of problem solving as a community of solutions. I don't know if that makes sense, but run with it. I don't know if that makes sense to you.
Say more about trust as part of the API. What are you thinking there?
Well, ultimately, if you have an inference, and this is a stream of intelligence, it's some sort of output of the model. If that had some sort of trust component built into that API, then any LLM that was reading that could understand that dynamically. Does that make sense?
I think, I mean, a little bit. What we're seeing, the models are pretty extraordinary. I mean, we have, for example, you can take a Gemma off the shelf, internally. And I thought, when I saw MetaLM and how it's, passing all these exams and it's fantastic in its diagnostics, you look at it and you're like, wow, is it a new model? Is it something new inside? Like Freddie said, is it a new technique? No, it's just being very painstaking about the data, right? And cleaning and feeding this. And what we're finding is that, patients now are starting to use this stuff, and we're saying don't use these because it's, it's probabilistic, right? So there's case after case you read about where my doctor couldn't figure it out. I went to ChatGPT, I went to someone else, and I tried this, and guess what? It found my issue, right?
Yeah.
And so I think we're going to start to, in other countries outside the chain of litigation that we have in the Western world, right? Because if it makes a mistake, who's going to pay for that, right? It's just that's just how we are set up as a culture. Other cultures don't have that. Other cultures, for example, in India and maybe places in the Middle East, are like, we're doing our best for everybody, right? And we can actually extend that care for everyone else. If we make a 0.0001 mistake, like a self-driving car has an accident, John, right? At least we did our best for everyone else. It's a different philosophy culturally, right? So I suspect those cultures may be first to using these things we talked about, where it's what's called an adjunctive opinion, right? An adjunctive opinion is, let me get an expert opinion, hands to the field nurse, and then she then makes a decision and the call for that patient, right? So we're putting in the hands of a field nurse is probably someone trained, in a local village about how to, do some basic care and triage, and she has access to the most sophisticated analysis in the world, right? And then she'll be able to take that and say, oh, looks like you actually have some precancerous thing. I can send you a referral, or you're fine, right? And I think that's where we're going to start to see where AIs with someone like that, right, will actually elevate care. But what the thing is, that back to John's point, is that it's a system, right? It's not log in, do this, send me the medication. It's log in, hang on a second, let's run it by Jonathan. He's taken the course on first aid. Like, oh, you don't need to have this high-end medication. You just have a headache, like, right? Right. So I think that's what we're going to see, James, is these techniques are super powerful, but they're really aiding the people in the field have nothing else to offer. Over time, as we learn as a culture, how do you accept that into more general care? So it's basically health and wellness, right, as well as financial, right? And that AI can do tremendous good, but it will make mistakes. It will call out the wrong shot, right? Guaranteed. So how do we deal with that as a culture, right? And I think that's really where I'm starting to see these things, James. And so the notion of trust in the API is almost like put a human in the loop, right? And that's your trust vector, right? And then how does a human trust another human? Validate, show me the research. So the AI will show you that. Here's the research I found. Here's my source of truth. Here's where I came from. But the source of truth is that if Jonathan's in the field, he took the first aid course. Do I believe this or not? I'm just trying to care for someone whose baby's crying, right?
This
Super good point.
Just to build on a little, this notion that you have somebody double checking the work is really important. And going back to Apollo and going back to the final trust in all those systems, they didn't trust anybody in the development of that thing. Like, no, actually, they probably trusted somebody, but there were probably very few cases where they actually trusted any one engineer's work. I would be stunned about that. Everybody was double checking everything. Everything was reviewed. Everything was reviewed in excruciating detail. People replicated calculations all the time. And so, even with humans in the system, you're not going to have full trust in many cases. Instead, you're going to construct some system where you're double checking each other's work, If you're trying to do something hard, if you're trying to work through a complex problem, like developing Apollo, you're going to develop schemes to double check each other's work, to build on each other's work. And I think that's going to look very similar as we start to incorporate AI into these processes.
It's really interesting. When we first started working with NASA, there are a few ex-Apollo people who are still kind of there, and I had the privilege of working with them before they retired. And that was one of the things that really struck me was this, we used to parallel path everything. That's what they said. So everything was parallelized. And that was just kind of like a sort of cultural behavior, which I found super fascinating, because that is not necessarily the way we do things at the moment, right? We don't build that redundancy into the system. We don't say, we're going to build this model, but actually we're going to build a completely separate way of doing it, because just in case we might need this other one.
Good points. I want to stay as much on time as I can for people and be respectful of everyone who's watching, listening now and later. We have two more tenets I'd like to talk about very briefly. Very briefly. Let's talk about tenet number 4, strict configuration control. This was also called out as an important part of the Apollo development. What role would this play as we think about how we should approach creating safe and trusted AI systems in the future? Anybody want to jump in on configuration control? And maybe, James, you can kick that off with how you think about that when you hear those words applied to AI.
Well, I was going to hopefully that Freddie, because I know that he's been building foundation models, and that this would be the one for him.
Freddie, what are your thoughts? Strict configuration control as you're building models.
Oh boy. I think that's your answer.
Oh boy.
So control is a funny concept. Control in the engineering sense is having a sort of a feedback loop where you have the output of the system kind of processing it, feeding it back, the output of that back into the input, and being able to sort of like manage how the system behaves based on its location, its parameters. I'm sure there are versions of that in machine learning. So we're still in embryonic stage as far as I see it, where I think because the way we develop machine learning, the paradigm, the most prevalent paradigm of machine learning, which is supervised learning now. Even unsupervised learning, the way we do it now, is really supervised learning, but except that the labels are kind of synthetic, is that they are sort of auto-generated, but it's still using supervised learning under. For those of you who are not familiar with supervised learning, it's basically you teach a computer how to do anything really by showing it, this is what this is what you look like, this is what's in the image, this is what's in the video or the audio, and then the machine is trying to predict that. So this kind of supervision has limits, because the supervision has sort of like parameters, because every time you say, okay, these are my data, these are the labels, the data come from a particular domain, but then if the parameters of operation change, let's say the machine learning is taking data from not an area that it's familiar with, then things are completely unpredictable. We don't really know what to do. We have specialized areas of research in machine learning where we're trying to mitigate the harm from those cases. And I think this touches a little bit on adversarial attacks and things like that. But it's because there's so many ways that the system can be operated outside of the parameters, outside of its comfort zone. And as I said, the complexity of the data is such that we cannot predict how the system is going to behave. So this is what I can say about control. I'm not really sure how to comment on strict configuration. But I think control is one of those areas where, as John said, because also in machine learning, we test as we fly. We can see how the system is performing, and based on that, decide to maybe take it offline, or let's say here's a new set of data that I hasn't seen before. Maybe try to learn from that continually. So there's like an aspect of continual learning that is applied on real systems. But there again, I think that risk is acceptable only in use cases where they're not safety critical.
Good stuff. Thank you, Freddie. Scott, did you have any thoughts on that tenet?
I'll just have to be brief given the time. So think of configuration control for ML as lopping off the squirrely ends. So think of like a distribution of how it performs, right? So for example, if you know a medicine works in certain areas, but these genomic variants are not so sure, you don't prescribe it for those because you don't know exactly the interaction, right? But you have really good evidence for that. So what configuration can do is start to lop off and say, this model is good within these operating parameters, outside don't use it, right? It looks like it may succeed, but basically what you're getting sort of squirrely results. And so you see this a lot in now basically a mixture of experts. You have multiple models that are good at different things, but they look at basically the weight distribution and saying, oh no, we don't really trust that answer. We're going to use this different model. And it can actually learn which model to use in which circumstance. So that configuration helps you then guide, even though it's a probabilistic answer. If you set that up ahead of time, you have much more confidence because you're not getting sort of these edge cases in that particular model, right? And so I think that's a nice way to think about configuration, of lopping off the pieces of the probabilistic space you don't really trust, and so you get much better performance of each of your different models. So I think that's really important now to think about as you're using AIs in these more deterministic systems.
Thank you. And I think this does feed into our final tenet today, which is extensive training and simulation. Of course, this would include training models on diverse data sets, running simulations to test models under different scenarios, and using synthetic data to mimic real world conditions. And we've touched on continual learning, and we know that and adaptation are key to making our models more robust. But when we think about extensive training in Apollo, of course, we're training the astronauts, but now we're talking about training the models. And when we think about simulation, we're thinking of the lunar simulator, the command module simulator, and other things that the astronauts had to learn how to use. But when we think about it for AI training and simulation, how do we learn from what NASA did with Apollo in developing our future AI systems? I'm going to ask John if he has any thoughts on this first. Having spent many years at NASA, you might have some.
First, quick thoughts, because of the time, is that they chose their battles carefully. Like they understood what are the things that are really critical to simulate. For like a landing, they might choose that it's critical to simulate the entire thing. Or they might choose to, really focus on a particular aspect. Also, they would choose the level of fidelity, both based on what was, achievable and what was valuable for achieving their goals. And I would say that's a piece to take, which is choose your simulation based on what you're trying to do. And it's not necessarily about simulating everything to the finest detail, but finding a way to really have design your simulation approach so that you are testing what you need and that the results are portable to where you're actually going to be applying this thing in the end.
Great, thank you. Freddie, any final thoughts on training and simulation and how we apply those learnings to AI development?
I think my mind's going to ChatGPT and the new iteration that will come within the next couple of years. I think when people say it's going to eat up the internet, it's definitely true. I think that eventually we're going to run out of the humanly created data to feed these models. So if there's anything extensively trained out there, it's definitely one of those models. But then, the question is like, is it's pervasively trained? but by extensive training, I think there are other parameters of the training set that we need to consider, like the importance of the different data points. Like the way the systems are being fed is kind of blindly, obviously there's a little bit of some kind of like a vetting going on, but when it comes to, we want to make a system that is, say, fair, not biased, be more aware of safety, then I think some data points need to be deemed more important than others. So I think the vetting process is definitely an algorithm to be considered when you decide what humanly created data you want to feed the next ChatGPT or whatever LLM. And then, there's talks about, eventually we're just going to be using data that the LLM itself creates, and then we're just going to feed it back into itself. Okay, I mean, that's definitely a reasonable concept, because we do it. We create our own data, and then we eat our own data all the time in our lives. This is how we learn. So I think there's like a continual learning aspect here, but there's something to say about the bias being propagated. If that seed of bias is there, or untruthfulness in the initial seed data, which is the humanly created data, then it's going to be propagated in all the synthetic data that the machine is going to generate, and then feed back into itself in future generations.
Great. Thank you, Freddie. Scott, what are your thoughts on this tenet? Or maybe on what Freddie just mentioned?
I think we've had a great discussion today. I think, Jonathan, you look across all different aspects of bringing this into space science. And I guess on an ending note, I would just like to emphasize that, as we're bringing these systems in, we don't really think about AI as a new type of intelligence that we're bringing into. And I think the biggest risk is for those that say, I don't want to use that, right? Because think of it this way. People in 6th grade now are using AI to generate images and cartoons and books, right? The next generation, and next year, Freddie talked about, if we have AIs now, the capability of a PhD, the space scientists who are graduating by 2030 will have had 5 years working with AI as a natural tool every single day, right? And we're dealing with slide rules today as the leaders in a lot of comparatively, right? So this is going to happen so fast. I think the whole thing for us, I think the message here is AI is coming. It's here. It's a collaborator in science. And the sooner we figure out how do we use this as a collaborator and deal with that as a new intelligence in space systems, the better off we're going to be. Right. And those that don't will be standing there in 2030 wondering, where'd all the business go? Right. And where'd all the interesting science go? Because I don't know how to do that, because I've never really had a calculator, never really had an AI as a partner. But that's how people are getting educated in the next 5 years. Right. And so I'm glad you did this today, Jonathan, because all the things we did for space science, but now think about that as a new type of person in this field, and how do we work with that? So I think Freddie made some great points. I didn't want to, I think he nailed a lot of that. Same thing with John. But that's the big point for me, is thinking through it, because it's going to come so fast.
And you've queued up nicely a wormhole topic that we want to do in the future, and that we have as a group talked about many times in the past, and that is the future of AI for science. So we can all look forward to a much deeper discussion right on that one topic, I think. And
we might need longer than an hour, though.
I think we might.
Be more than an hour.
Yeah. So James, how about some final words before we wrap up today's wormhole?
Yeah, I just wanted to say this has been awesome on so many levels. You guys have given me about 3 different new ideas for things, and just really deeply appreciate spending the time. So thanks so much. And again, for everyone watching, I hope this was inspiring. We really are trying to figure out what state of the art looks like. And this means, of course, high TRL applied AI that actually gets used and can actually make a difference, both for space exploration, but also how we manage our planet, but also keep ourselves healthy. These are all things we really care about, and it's discussions like this which help us get to that vision. So yeah, Jonathan, I'll hand the mic back to you.
Great. Thanks, James. And thank you, John. Thank you, Freddie. Thank you, Scott. It's always a pleasure when we have a chance to talk as a group like this. And thank all of you for joining. It wouldn't be the same if we didn't have those of you who are both here live and the many more who will be listening to this on our podcast. We're looking forward to the next Wormhole. Please subscribe to our podcasts on any of your favorite platforms. We'll talk to you again soon. Now, one final thing is we do have another thing coming up this week, as a matter of fact, at 9 p.m. Pacific time, 12 p.m. or 9 a.m. Pacific time, 12 p.m. Eastern time, the AI State of the Art Showcase, where we will be looking at the 2024 research projects from our FDL cohort. Very exciting work around heliophysics as part of FDLX Heliolab. So there is a URL here on the screen. You can find this link on LinkedIn. We'll put it in the chat here too. I believe we'll be able to do that before we actually wrap up. Or you can just go to, James, what's the primary URL people can go to?
It's not difficult to remember. FDL.ai. That's the easiest one.
There we go. FDL.ai.
Can I do a quick shout out to this? So if you are interested in high TRL AI, you probably know that continual learning is still in its infancy. In fact, there really aren't many examples of applied continual learning, but we have a lot of that at this showcase. So if you really want to understand how AIs relearn as they interface with reality, please check it out. It's totally cutting edge stuff. And of course, if you're interested in the relationship we have our planet with our star, we're going to be covering that as well. So yeah, it's going to be an exciting session.
Great. Well, as always, thanks to our partners, Google Cloud, Pasteur, NVIDIA. We couldn't do it without you. And we'll look forward to the next time you engage with us here on the Wormhole, produced by the NASA FDL. Thanks very much, everyone. We'll see you soon.